All right. So good afternoon, everyone. We have Professor Sanghyuk today, and he'll be speaking about endpoint eigenfunction bounds for the Hermite operator. Professor Lee.
Yeah, thank you. Thank you for introduction, and thank organize for invitation. And I can see some of you, but I cannot see clearly. Anyhow, so can I start?
At the end of the talk, maybe we will zoom it and you can see some of us. I'm Rahul from Bhopal.
Oh, yeah. Good to see you.
Yeah, good to see you too, Professor.
Can I start?
Yes, please.
Yes. Okay, so okay, this is joint work with my collaborator, Ernie Chung from Jeonbuk National University, a south part of Korea, and also Jae-hyun Ryu. He's working in the Korean Institute for Advanced Study. Okay, so I want to start with a brief introduction to the Hermite operator. So I picked dimension bigger than or equal to 2, and the Hermite operator is differential operator with minus Laplacian, and also here the potential term, quadratic potential. So we're working in a RD, and this operator has a discrete spectrum. Discrete spectrum, so even positive integer plus dimension d. Okay, so the multi-index, which is contained in this d tuples of integers, including 0. So the pi alpha denotes L2 normalized Hermite function, which is the eigenfunction of H with the eigenvalue 2 plus 2 times alpha, absolute beta alpha plus d. Here this is the just typical notation. Okay, so then the set actually forms a also normal basis in L2. So we have the Hermite expansion. So this is very standard. So any L2 function can be expanded as a Hermite for the expansion of Hermite function. Okay, so then the pi lambda denote the spectral projection to the vector space spanned by eigenfunctions with eigenvalue lambda. So more explicitly, we can write this way. So because this guy is eigenvalue and the eigenvalue have this value lambda, so we collect all these Hermite functions which has the same eigenvalue. Okay, so we we are interested in the operator norm of Hermite spectral projection operator. So we denote for any given operator T, we denote the norm of operator T from LS to LR by this notation. So norm of operator from S to R. We are mainly concerned with the optimal bound on the operator norm. So the from L2 to LQ space. So here Q is assumed to be between 1 and infinity. So and also we wanted to figure out what is the optimal bound of the operator norm in terms of lambda up to a constant factor. Okay, this problem in one dimension is actually trivial, almost trivial. So optimal bound can be easily obtained by using the LQ norm of the Hermite function in RD. So nothing serious there. But this sort of operator norm was studied in connection with the Bochner-Riesz summability of the Hermite expansion. Okay, so this is the Bochner-Riesz mean. So whether this mean converges to LP in as R goes to infinity is the convergence problem, and which was studied by S. Wenger a long time ago, and later Karadijov and Dankavelu. And there are more recent work by some authors. Okay, so and also the bound independent of lambda, the independent of lambda, the bound over this on this independent of lambda also has an application to the study of a strong unique continuation problem for the parabola equation. So such work was done by S. Kauriasa and S. Kauriasa Vega and Koch, Tataru, and recently, I and my collaborators. Okay, so to explain the problem, which kind of endpoint estimate I wanted to talk about. So I wanted to briefly review the previous result. So delta RS denote the difference between of two number, one of R and one of S, and the Q0 is the particular number. This is this number 2 times t plus 3 over t plus 1. So by the work of Karadyzhov and Koch and Tataru, it is known that for Q, which is not equal to, except the number Q0, this particular case. So the operator norm is completely characterized. So between when Q is between these two number, the power, the lambda to this power is optimal bound of the operator norm. And also here, in this range, so this Q0 is this fixed this number. So we have this bound, and also we have this different power of the bound here. So, but here the thing is that we do not have the bound when Q is equal to Q0. So this Q0 is missing here. Okay, so and also I just wanted to emphasize this is equivalent, right? This is comparable to. So, but the lower bound is much easier to prove because we test the inequality with the special functions with the choice of special function. So you can test the inequality, then you can show all these bounds are sharp, even including the Q0 case. Okay, but the difficulty is in proving the upper bound of the operator norm. Okay, so this might be illustrative if we consider the operator norm in this way. So we are looking for the optimal beta. So beta as a function of 1 over Q. So if we draw the picture here, so this axis is 1 over Q axis, and the beta is the power of the of lambda, exponent of lambda, right? So in this region, we have this power, in this way, and also in this range, this is this range we have the bound like this, and also this range we have a bound this, but this red point is missing. We do not have a bound there. So that's the endpoint case I wanted to talk about. Okay, so the main result, our main result is the proving the missing endpoint case. So, but a previous result by Koch and Tataru, which I explain very soon. So by using the localized estimate over NLI, so it can be shown at the Q0 case, the critical endpoint case, this bound. This extra factor is we do not want to have this. But in one-dimensional case, it is known this bound actually fails without this logarithmic factor. So in one-dimensional case, we need that. But in higher dimension, when dimension is bigger than or equal to 2, it was conjectured by Koch and Tataru that the natural bound, so without the logarithmic factor, this bound is hold. Okay, so and this bound is very significant because once you have the the bound here, this is a conjectured bound, then the interpolation with the non-bound actually recover all the previous result. Okay, so our main result is when dimension is bigger than or equal to 3, so we have this optimal bound. This is our result. And we also expect the same continue to hold when dimension equal to 2, but our current argument actually does not cover the case, so it remains open. Okay, so now I wanted to explain about this localized estimate. So localization near the sphere with the radius square root of lambda. So the symbol of the Hermite operator is given by this. So in the phase space, the eigenfunctions with the eigenvalue lambda, which I concentrate near the bigger one neighborhood of the sphere, yeah, bigger one neighborhood of the characteristic set, this set. Okay. This means the eigenfunctions are essentially supported in a ball of radius square root of lambda. So actually, if you compute the kernel, it actually rapidly decay if you go away from go outside of this ball. Okay. And also, if you compute the kernel explicitly, and the kernel actually shows different behavior when we cross the set, this sphere. Okay, so we wanted to concentrate it near this sphere of a radius of square root of lambda. Okay, so okay, so we to deal deal with that part that part, we consider dyadic decomposition away from this set. Okay, so for that we need to introduce some notations. So mu for the rest of this talk, this is dyadic number with the negative integer exponent here. And we define a set. So here, this is analogous. This analogous with the thickness mu, and very close to 1, right? And our mu will be very small here. And if we have positive, this means you have inside of the sphere. Right, then negative means the outside of unit sphere. So then this set will be dilated by factor r to the 1/2. So this is very large analysis, but it starts from the very thin analysis near the unit sphere. So then we dilate it, right? So then plus means inside, and the minus means the outside. So because a plus is more important, negative is not so important. So the estimate over the outside region is much easier, and also decay is way better than the inside. So the important part is inside. So also we fix we simplify notation. The characteristic function of these analysis, dilated analysis, we denote that by this guy, so simpler by the notation. Okay. Okay, so this is the picture. So here we have we have here big the sphere along here, right? And then we decompose in dyadically. So And as the mu gets smaller, we get close to the sphere, the d minus 1 lambda, right? So then here, this guy is inside inner annulus. This is outside outer annulus. Okay. So we will compute. We try to compute the estimate over these regions. Okay. Okay. So the result due to Koch and Tataru. Also, even before there was a result by Dankabel a long time ago. This result, actually can be summarized in this way. So here is the theorem. Dankabelu case is corresponding to the mu is equal to 1/2. So away from the sphere. In that case, this result goes back to the Dankabelu a long time ago. But the Koch and Tataru, they did a more careful analysis, and they computed the operator norm over this annulus, inside annulus. Okay, so then they approved this estimate here, and then the exponent here. So I redraw this picture, which I already showed. This is the picture here. So this is these lines are the bound for the actual projection operator, but by the localization, dyadic localization, you have a different exponent. But the range now actually divided into only two regions here, just one region here and another region here. So, but this one carries some extra factor depending on the thickness of the annulus, right? So this operator, you can sum up, and you can sum. So this solid line actually shows the exponent of lambda power. This guy, if you remember, the exponent in the previous slide, then this corresponding to this. So if you add up all these estimates for the Q between this range, right? Then you can sum up only this exponent is positive. So that means you can get the estimate along this line, except this point. But you can sum up, with the loss of some log extra factor. Okay, so and also you can look at the other exponent, the other estimate here, right? So this one, and if you wanted to sum up along this dyadic number to recover this operator, then you will this part you can sum up, but this you're gonna miss this point because you cannot sum up there, right? So so that's why they couldn't get, but this estimate was already proved by Karadjov a long time ago. So once you get the estimate, then you can interpolate, then you can recover some other estimate. Okay, so and also, but this is not complete because we only consider the estimate inside the annulus. So we need to prove estimate which also the outside annulus, right? But that is much easier. So the estimate for the outside annulus is less important, and this can be done in many different ways. So maybe the easiest way is using kernel estimate, and the kernel corresponding to this operator is rapidly decreasing, actually exponentially decrease. So we can prove the estimate like this, right? So this is somehow TT star form. So it's a slightly different, the form which appeared here, right? So I will explain this later. So, but this is much easier to found, and the bound also hold for any m. So it's rapidly decaying away from the this sphere of radius square root lambda. Okay, this is the inside region. Inside region is actually the mu is smaller than lambda to the minus 2/3. So outside and inside and outside together. This very thin neighborhood of unit sphere, the sphere of radius square root of lambda. So that means this is big O lambda 1/6 minus 6. Okay, sorry. Minus 6. Yeah, 1/6 minus 1/6 neighborhood of this guy, square root of lambda as d minus 1. This is the region. This part also not difficult to handle. And on this region, we have this bound here. Okay, so as I already explained, because we have all the correct bound, the outsider and also very close to the unit that's as lambda to the this region, so very close to this, we have this. So we only have to think about the other part, right? So the inside analysis. So because of that, I mean, using Coca-Tatar result and the summation along the mu give the optimal bound, except this point, except. Okay, so then the other estimate we can be recovered by interpolation. Okay, so is that clear to everybody there? So I mean, is it allowed to ask question?
Yeah. Anybody, any question? I don't see any questions, so please continue.
Yes. Okay. Okay. So now, so our goal is to prove the missing case. So the localized estimate, which is by the Coca and Tataro, that is not enough to get the missing endpoint case. And we already also see that the region, the estimate, the outside region, outside of this region, this outside region is already well understood. This part, and also this very thin, the small neighborhood of this also very well understood, right? So we wanted to concentrate the inner side of the analysis, the sphere, right? Okay, so
you go to the next slide.
Okay, so I wanted to explain that. So then the issue here is sorry?
I was, the previous slide. Could you just go to the previous
Here?
slide?
Here?
Yes.
Yeah.
No. The next one.
This one?
11.
11. Okay. This one? Yes.
No, this is 9.
11. Okay.
Yes. This one.
Yes, this is 11.
This is.
Sorry?
Yes, this one here.
Yes. Yeah.
So I don't understand. So what happens at Q0? Could you explain? I think
In this case.
Something. Yes.
In this case.
The last point which you have written.
So this estimate actually equivalent, right? I mean, by TT star argument. So you can have lambda and lambda 3 and 0, and because this guy is the same, right? So this actually same with the 2 P bound and P prime bound. So actually I changed the exponent from Q to P. So, but this is the equivalent estimate. So you have to divide in half. So D over, sorry, D3 over delta P minus P minus 6 over 1. So this is TT star argument. So you have two couple of this two operator. So this is one from. Okay, this yeah, because this is not written in the form of L2 to LP bound, right?
Yes, and
Yeah.
no, what I was asking was this: what estimate do you get at Q0 by using this interpolation? That log kind of growth?
I mean, you can directly add up the estimate because you have this estimate here, right? You have this bound here, right? So when you try to add up this estimate, right, along mu, you do not have to sum up all the way. I mean, to the very small number, like so you can stop where the mu. So you only have to add up. So mu is bigger than lambda to the 2 over 3, right? So this only produce log power. So there are not so many, right? So this, I mean, if you just try to sum up, then you can sum up when this exponent disappear. I mean, this exponent until this exponent disappear. That's the point here. If you add up, you still have this bound, but you're gonna lose some log. I mean, because you have log many, I mean, mu there, right? Log lambda many mu there.
Thank you.
Okay, so so then the previous result, I mean, actually cover the case. That gives the optimal bound for this operator and also this operator. So this can be this part can be covered by Dankabell result. I mean, a long time ago, the result actually shows this, and this one is outside of the region, so we don't have to care about it. So we only wanted to consider. We only do consider this region, this operator. So this is the inside and also very close to the unit, the sphere of a radius square root. Okay, so then by duality, yeah. So I mean, this is trivial thing. This is operator and the Dior operator. And so you can, yeah, L2 to L2, you just move another operator, which is typically this is called a TT star argument. So these are all the same, right? So and also this projection operator is self-adjoint. So this is same, and of course the twice product of that is actually give the same operator. So this operator can be written in a form of this. Okay, so this is I mean where the estimate which I showed appears. So then instead of considering this form of operator, localized one-side localization, we wanted to get better. I mean, maybe we can get a better estimate by a two-side localization, right? So then we try to prove this sort of estimate on this sort of operator as many as possible P and Q, right? So, but the TT star argument, L2 to LQ estimate actually corresponding to the case P equal to Q prime case, right? But we wanted to prove many estimates, not necessarily restricted to this condition, right? So we wanted to get away from the L2 theory, so allowing various exponent, right? So But this sort of estimate also can be some of them can be deduced from the L2 estimate, because so this is trivial, right? So actually this is same with this. So you can split this operator. So this vector, and this vector, right? Because square is there. So then you can use the previous bound, which was obtained by Koch and Tataru, right? So this part and this part, you can apply that. And this basically same estimate, you can dualize it, dual operator. The dual of this, you can get something like this. So then you can get this estimate. Okay, also, I mean, this bound actually optimal because when mu and mu prime, mu and mu tilde is compatible, because if we go back to the previous theorem, Koch and Tataru, so I only mentioned this upper bound, but this is actually true with this. This also can be shown with with some examples adapted to the thin annulus, right? So that means when mu and mu tilde is compatible, you cannot get better than this. This is the best possible, right? So and also, and there is some sort of interpolation argument, right? You have a many estimate, and then probably you can add up these I mean estimate using some clever interpolation argument, right? But I don't think I tried such argument for a while, but that was not so successful, right? So then another possibility is what if these are not same? So if these are not compatible, right, then there may be some improvement of bound. Improvement means possibly you can get some bound better than this. So right, that was my idea. So then actually this is the case. So which I named the asymmetric improvement of the bound of the projection operator. So so here the dimension now is bigger than or equal to 3, and these mu and mu tilde, these dyadic number are smaller than or equal to 1, and we restrict this mu and mu tilde in this range. So this is enough for our purpose. Okay, so then if Q is between these two numbers, then we have the bound which is better than the previous one. So this is the optimal bound, which I showed in the previous slide, but we get the extra power of improvement. So here, so mu tilde is a smaller than or equal to mu, right? This restrictor. So so we have a slightly better bound than the previous one, which we get from the L2 bound. So of course, this C, the constants are independent of mu and mu tilde and the lambda. Okay, so this tells us the bound get better as the ratio between mu and mu tilde actually get larger, right? And also our proof of this estimate. This estimate actually recover this earlier result Koch-Tataru due to Koch-Tataru, which actually corresponding to case of mu and mu tilde are comparable to each other. But I will explain how we can prove this. But the getting this extra TK, I mean extra factor of improvement is much more complicated. Okay, once we get this improvement, then the endpoint estimate is quite easy to obtain. Okay, I wanted to explain that now. So the reduction, which I explained in the previous slide, so we only have to consider this operator. This operator means not very close to the sphere, and also still stay away from the center of the sphere, right? So then we decompose this operator in this manner. So you have actually double sum here, sum here, and double sum here. I rearrange the sum like this way. So depending on the ratio between these two dyadic numbers, you have, so it has to be minus here. This is something's missing here, minus here. So here, so we have this guy, I mean, dyadic number, and the restricted. The ratio is comparable to 2 to the k. So here the k is an integer. It could be negative and positive. It could be any number. So, and also mu and mu tilde is restricted. We rearrange the term in this way, right? Then also, and there is also improvement of the bound of this factor when this ratio, I mean the mu tilde is bigger than mu, because the operator have the same norm. The adjoint operator of this guy is lambda mu tilde, right? Plus, and this is the adjoint operator, right? So mu, because of that, you can switch this role of mu and mu tilde. So with that, you get also you get improvement in this case, right? So if you apply that, then this ratio, actually the ratio of these two numbers is fixed like 2 to the k. So you get this extra dk, I mean extra factor, and also you get this, yeah, this power here, right? So then, and also the factor appearing, this guy, right? This guy, the factor appearing here, it is a disappear, right? Because of our exponent actually gives this everything is equal to 0. This factor disappear here. So that's why we only have this one and this one, right? So then, because these analysts are all disjoint, right? So because of disjointness, this norm of the operator is bounded by this guy. So each of these operators actually supported in a different dyadic shells. So you can, this guy is bounded by this, and we use this improvement of bound, and this the optimal bound here, and then we got this, right? Then again, this guy also have a disjoint spot, right? So therefore, we can control this guy with the LQ prime norm of so what I mean is this sum is also bounded by LQ Q0 prime norm or LQ0, right? So they all together, we get this bound here in the end. So we get this bound, right? Then the only thing we have to do is just a sum over k. This gives the endpoint, the missing endpoint case. Okay. Okay, so but this could also used to get a stronger estimate, which is called a weighted estimate. Here, this also conjectured by Koch and Tataru in their paper. They used the weight function like this. This weight function actually mitigates bad behavior near the sphere. The sphere t-1 and this sphere, right? So this actually killing some bad, I mean, because this is getting smaller near that region. Okay, so then also the gamma given by this number. This number, I don't want to read all this exponent here, but this is the number. Okay, then, so we put the weight function here, this weight function. So the inside, actually, inside of this region, this actually survivor, here we have factor here. right? This is inside, only have influence in inside, and this have outside. In outside, you can add a big weight, right? Weight could be very large. It doesn't matter because the kernel actually decaying very rapidly, and the estimate is still very good. So you can add any power that inside the power is already, fixed. That is also sharp. You cannot get better than, have a better exponent that. Then you can get this estimate. And this one also contains the main theorem, because if we take a particular case, Q equal to Q0, then the gamma is equal to 0. So therefore, this guy become, because you're actually putting power here, 0 power, that means this become 1. So this guy is 1, and this guy is bigger than 1. So you can dominate this guy with this guy actually in that case dominate the projection operator. This can be done, right? So therefore, this implies the endpoint case. Okay. So this is the all about our result. So now I wanted to explain the how to prove that. So this proof starts with some very nice representation. Nice formula for the projection operator that is related to the Hermite-Schrödinger operator. So the Hermite-Schrödinger operator is the operator given by this formula. This formula. So you can directly check this is solution to the usual Schrödinger operator, which is given by the Hermite operator and with the initial value f. Okay, so and also when f is contained in Schwarz case, this sum uniformly converges for any t and x. That's also very easy to show. So here, so because the Hermite functions are eigenfunction with eigenvalue, this eigenvalue, right? So we can write this way, right? Then we actually integration by part, we moved this operator back down here. Then the Hermite operator or LP normal for Hermite function also bounded by this way, this for some, but we don't want it to have a precise one. This is enough. So, and also this function is trivially contained in Schwarz class, right? So therefore this norm, this guy is bounded by this exponent. So taking n very large, you can show this series converges uniformly, right? So this convergence is very good for any Schwarz function. Okay, so then we can prove some a priori estimate. Once we get the a priori estimate, we can extend that to LP space by density argument. Okay, so here and another important but very simple observation is, so this guy become a delta function. So here the lambda and the lambda primes are all eigenvalue. The eigenvalues of the Hermite operator. Because these are the difference between these two numbers are even integer. So because of that, this becomes delta function. So this is a very special property of the Hermite operator. So then we can write, this Hermite projection operator in this series. So actually, only one survivor here because of this relation, right? Then this operator, these guys, this can be written as a Hermite operator, Hermite-Schrödinger operator. So we can write in this way. So here, so then we can use a Malus formula for this operator, this part, right? So we have a very nice formula for the Malus by Malus result. So we have the expression like this. So then we substitute this formula inside the integration. Then we got kernel representation, a very nice formula for the projection operator. Also here, this solution looks similar to user Schrödinger operator, but this amplitude, I mean, this function has this factor here, sine to the, yes, actually have a singularity, 0 and at the pi, and every periodic point, it has a singularity there. Okay, so but in our case, we only need to consider the interval here in this region. So because of that, we have to concern about have to be careful about the singularity point when minus pi and the 0. That's the point we need to pay more attention. Okay, so here, so these properties are easy to prove. So because this, I mean, phase function is given like this absolute value, scale of absolute value, and the inner product. So all these are invariant under rotation. So because of that, yeah, you can easily see this guy. The phase functions are actually, I mean, the same under the action of rotation. So simultaneous rotation, both variable, you have rotate, then you get the same operator. So, and also for the rest of talk, I mean, throughout this talk, I will denote the kernel of an operator is a simplified notation, like a TXY means the kernel of operator. So then by this relation here, you get this one. So if you rotate, the kernel of projection operator also have the same property. So you rotate here, and the simultaneous rotation actually preserve the kernel. This will be very useful whenever we try to normalize the positional function. You can rotate together, then you can push the function, support the function into certain, nice position. We will use that. And also this can be reformulated in this form, these composition with the rotation commute with the projection operator. Okay, they probably not so important, but this was already observed a long time ago, Koknev. So this person used some very special properties of a Hermite operator. Okay, so as I already mentioned, this operator has this A has a singularity. So we need to decompose, this operator in nice way. So we wanted to break this operator decomposing away from the singularity. So here the singularity of the A is 0 and the plus minus pi. So for that we use a typical function which satisfying this and also supported here. Right, then we decompose near the origin, near the 0, near 0. This is near 0 and near pi and minus pi. This is periodic, so you can identify these 2 points, right? So you can decompose in that way. So this one-sided, this is above 0, bigger than 0, and this is from the negative side actually approaching to the 0. So we have the similar decomposition here. So then, but the remaining part we just put psi 0. That means psi 0 actually stay away from any singularity, 0 and the minus pi and pi. So this is a very nice function actually. So because of that, that part is much easier to handle. Okay, so then we define an operator for each eta supported on this interval. Okay, so we define an operator like this, putting eta here. So if you put a characteristic function, of this interval, then you're gonna recover the projection operator. Okay, but so then we replace the characteristic function with these whole expression here. This expression we put inside here. Then you're gonna break this operator into this these form of operators, right? So then we wanted to prove estimate considering each of these operators, Okay, so that's what we wanted to do, but there is some good news because there is some symmetry. If you remember these phase function are given by sine and cosine, right? So because of that, it has a very nice periodic structure, also some sort of symmetric property. So one of them is like minus t give this, and a translation by pi and the reflection actually given this sort of nice property. And also these are integer point, right? So these factors can be removed, taken out. So it doesn't have any serious, problem. So because using the symmetry, you can easily realize the bound. You can deduce bound from this bound on this. You can deduce bound for this guy, this guy, this guy. So therefore, you only have to consider this guy only. You don't have to worry about the other guys. So and also this is much easier. This part is much easier because it doesn't have any singularity in its port. So yeah, but still you have to do some work, but this part is much easier. So now let's consider, only the important part here. The other part will be handled by symmetric property. Okay, so this procedure, now I change notation a little bit here. So this is very supported in an interval of length 2 to the minus a, comparable to 2 to the minus a, very close to the origin. Okay. So that's what we wanted to do. So the idea is to prove each estimate for each of these operator, and wanted to add up together and try to recover the estimate. Okay. So do you have a question? Yeah, please ask if you have any.
No, I don't see any.
Okay, if not, I will continue. So this kind of decomposition actually give very easy proof of the all the result, which is due to Karadyzhov. Karadyzhov, he proved the uniform bound. Uniform bound means the bound which is independent of the lambda. So in the picture, there is the region where the point where the line this line touch the x-axis, right? That's the point here. So this is a Karadyzhov result. So I wanted to prove this result as a warm-up. Using the decomposition I just introduced. So we have we have this formula here, right? This projection operator here. So then we use isometry of this Hermite Schrödinger operator. So then just simple application of this isometry, and also Minkowski inequality key L2 bound is controlled by this, right? This is actually very trivial. And then we have L1 to L infinity bound. That is a size. L1 to L infinity bound is controlled by L infinity norm of kernel, right? The kernel, if you remember this, so the kernel of this guy has oscillatory factor plus oscillatory factor times, and there is a there, a here, right? This a will be decomposed, by this precise a, means this size actually give on this region 2 to the minus and 2 to the j over j times d over 2, right? But the interval length is like 2 to the minus j. So altogether, you're gonna get this bound here. So, okay, so then you interpolate all these two estimate. Then you have a many estimate along this held conjugate exponent. Then you apply the TT star argument, typical TT star argument. You get this bound here. Then you also have another bound by duality. So duality means a dual exponent. Then you get many estimate inside inside this cube, which okay, so I'm gonna have this. So you have originally you have L2 estimate here. So then here this is 1 over infinity estimate here. Then interpolating, you have many estimate along this side. Then you use TT star argument. You got something here. Then duality gives something there. So if you interpolate, you're gonna get, I mean, this estimate, the estimate on this region. This picture is not so nice, but okay. So okay, so let me correct it. So a little bit. So you will have the estimate. I mean, all the estimate. These estimate. So the precise form of estimate is like this. So you have this form of estimate with the exponent, and also all the p 1 over p and 1 over q. Oh yeah, here 1 over q, and this is 1 over p. Okay, in this region, you have this bound. Then particular, I mean, we wanted to prove the estimate, adding up the estimate, especially on this point, right? So this can be done by simple summation trick, which is called the Bourgain trick. You can add up. So here in this argument, I mean, so what I wanted to emphasize is the importance of the L2 estimate and the L1 to L infinity estimate. If you have a correct estimate for these two cases, then by interpolation, you can recover many other estimate, yeah. So that's what I wanted to do, I mean, with that operator, I mean, a symmetrically localized operator. Okay, so this idea will be used throughout the rest of this talk. Okay, so just remember, you need L2 estimate and also L1 to L infinity estimate. Okay, so to make the argument simpler, we actually rescale the operator. The rescaling actually make the problem simpler because if you remember the phasor function already, so I'm going to explain that, but we actually
go to the previous slide, please.
Mm-hmm.
Okay. So here P and Q are in the, I mean, by interpolation, how you get P to P prime, right? And then you use the TT star thing, is it?
Yes, TT star argument.
Okay. Oh, yes, you've written. Okay.
So yeah, at the beginning, I mean, from the beginning, you're gonna get something here, right? Then also you get another estimate here. Then you interpolate. Sorry, I destroyed the picture, but probably I can recover it when doing. Okay, so you have estimate here, and you have estimate here. Interpolating, you get estimate along this diagonal. Right, then you use TT star argument, you will get the estimate here, right? Then dualize, you get here. The interpolation will give the quadrangle region, the estimate over the quadrangle region, right? So this with this exponent. Is that clear?
Yes. Okay. Thank you.
Okay. So then we, instead of the considering original operator, we rescale. I mean, we consider rescaled operator. So we consider new operator by rescaling kernel side here. Yeah, we actually expand. Then this rescaling doesn't have any harm. I mean, doesn't have any influence. Just the constant multiples of the certain power of lambda will appear. Okay, so we're gonna prove the equivalent estimate. You can go back and reverse rescaling, then you recover the estimate for this guy, right? And also we rescale it, and then we also rescale, I mean, this decomposed operator. Here, the A mu plus, I mean, now I wanted to simplify this because we rescale it, the a sphere of radius square of lambda now become sphere of unit sphere, right? Because we rescaled it. So we wanted to simplify the notation and putting this is analysis of analysis given near the unit sphere. So I wanted to simplify. This is analysis. Okay, then with the quantity, the bounding quantity now changed. But if this also scaling, just scaling. Okay, then we have the same assumption here. Then we have this. This is basically actually same estimate which I showed in the previous slide. Just a rescaled version of the previous estimate. Right now we have a unit. I mean the analysis close the unit sphere. Both are unit sphere. Okay, and also here this is the notation. This was the characteristic function of this analysis here, right? But now I wanted to simplify the notation here. And also the PQ, the range of this actually satisfying this condition. Yeah. Okay. So, but this one actually even slightly bigger than the theorem. I mean, bigger than the one which I showed in theorem. But the problem is I only mentioned in a restricted region. Yeah. But because of this factor, I mean. So to get the certain uniform bound, you have to make this guy equal to 0. So the important thing is the case this is equal to 0 means so this is important because in order to kill, I mean, this exponent appearing here, the only most important case is this case, p plus 3. So delta p and p prime. This case, yeah, certainly this case is included in this range when dimension is bigger than or equal to 3. Yeah. When 2 is equal to 2, it's not contained. That's why we have to exclude, I mean, the two-dimensional case. This will become clear later. Okay, so yeah, so now we reduced everything, I mean, to proving this estimate here. This is what we wanted to prove. Okay, so then I wanted to do a lot of reduction to prove that. So here, the important thing. So because we basically rely on the interpolation between L2 estimate and the L1 to L infinity estimate, so we have to be able to get the correct power of exponent here. So if you put 1 infinity here, then the right exponent is lambda to the minus 1/2. So you have to remember this exponent and also this power. This one is not so important somehow because we're gonna get much better estimate than this. Yeah, that will be combined. I mean, actually put into the extra gain of the bound. Okay, so because of that, the important part is getting correct power in terms of that. Okay, so now because we have a scaled operator, so we scaled x and y by square root, right? So before in the previous slide we have lambda here, right? So something called a pi, that was a pi lambda x y s. Lambda was down here. But we scaled it, putting lambda, extra lambda here, and the lambda here, because of scale root scaling. So then we take out that lambda here, taking this out. So now we have a bit simpler phasor function. So we have everything, I mean, it's just compact set and the lambda, but the lambda is taken out by scaling. That's why we perform scaling. Okay, so then we have a phasor function here in this form. Okay, and we wanted to obtain the correct estimate of lambda to the minus 1/2 for L infinity L1 to L infinity bound, and this one. This is typically typical power when you're considering the oscillatory integral of this form. I will explain this later. Yeah. Okay. So to get the correct decay estimate for the kernel, right? Because this is integral along S. So you wanted to use a Van-der-Kolk lemma, right? So Van-der-Kolk lemma or typical.
So just one, the scaling is in only X and Y, right?
Yes, right.
Okay.
Yeah, okay. So
but there was no lambda factor in cotangent?
The original form, I'm gonna show you what was the original form here. So this was the original, yeah, phase function, right? So lambda was only here, right?
Mm-hmm.
So then I scaled, I mean, put extra lambda here. So then you take out all the lambda, I mean, okay, still here, you're gonna get this. The typical oscillatory integral. Now it looks like, yeah, it actually become a typical oscillatory integral.
Yeah.
Okay?
Yes, thank you.
Okay, so yeah, the first step is taking, I mean, considering taking derivative of the phase function, right? So we know the Van-der-Kolk lemma. So because of that, we have to take a derivative of the phase. So first order derivative. So if you compute the first order derivative, you get this very nice formula. So sign down here, and here the Q is a quadratic, the second order polynomial. I mean, so here this you can write this one in nice form. I put dxy because I mean dxy is this function. This is actually discriminant of this, yeah, this quadratic equation. So this is a simple computation. You can easily check that, right? So so then the stationary point is actually determine the behavior of the oscillatory integral. So the stationary point will be given by the zeros of this function here. In the position of tau, now you have a cosine here, right? So that actually make the structure a little bit complicated, but cosine is still a quite nice function, so it doesn't really give a serious problem. Okay, so here I mentioned, I put this kind of things here. dxy determine the nature of the stationary point. So that means if you have a multiple zero, right, or in that case, in such a case, it may have the stationary point may be degenerate. But if these zeros are stay away from the origin, and also the well distanced means this quadratic equation has distinct two root. In that case, the point, a stationary point, are non-degenerate. So non-degenerate means the second order derivative survivor. So then Van-der-Kolk lemma will give you the power of lambda to the -1/2. Okay, so this quantity dxy, which determine the structure, I mean, which determine the structure of the stationary point, right? That is important when you try to handle the oscillatory integral with the first order derivative. Okay. Okay. So then I rewrite the dxy in this way. This is very simple. I mean, trigonometric simple thing. So it's because you have here inner product, you rewrite those things in this way. So inner product, cosine function appear, then using the simple trigonometric identity, you get this. So the reason why I write this one in this way, because is here. So if X is contained in annulus here, and Y is contained in annulus here, in that mu and mu prime, mu tilde is very small. That means very close to, I mean, the pointer very close to units sphere. So then this guy comparable to 1, actually close to 1. This guy is close to 1, right? But this one is comparable to mu, right? So you factor, and the distance is comparable to mu, and this is comparable to mu tilde, right? So you have a mu quantity comparable to mu and mu tilde here. This is mu and mu tilde. And then this guy is comparable to 1, basically. So the angle will determine, I mean, the value of the discriminant, right? So we break, I mean, we wanted to decompose this annulus into the some sort of angular sector, which in which we manage to control this separation angle between each decomposed pieces. So, but here, if the angle is too large, if angle is too large, right, then the estimate is very easy, because this guy is very small, but you have a very large number here. So discriminant is always bounded, I mean, away from 0. So the behavior of the oscillatory integral is much easier to handle. So let's get rid of that case, and because then we may assume this angle is very small. Very small means we have a two thin analyze, but this angle between the two portions is very close to each other. So we localize the integration region in this way. So here E1 is the standard basis. I mean, this is sitting on the unit sphere. So we only consider a small portion of the annulus here and also annulus here. So this is a very easy reduction. So okay, this is very easy reduction, but you have to do some work. But it's not, yeah, there's nothing, yeah, serious there. Okay, so then we decompose it. Decompose that small, I mean, area. And area on the analyze. So here we have two analyze, then we break that into the angular sector, so that each of these angular sector has diameter comparable to 2 to the minus nu, and also these guys, the angular distance between comparable to the 2 to the minus mu. So this is something called Whitney type decomposition. So I bring in I consider this as d minus 1. We make a Whitney decomposition away from this diagonal of this set. Actually, we wanted to put the A0 here and also intersection A0 here. So that means small cap region, we decompose this set using Whitney decomposition. Then we project, I mean, this set, the annulus, into that angular direction. So that will give this kind of a set decomposition. This is a very commonly used many cases when we try to handle the bilinear operator, something like that. Okay. So, and also here, this is probably not so important, but we stop decomposing, I mean, this Whitney type decomposition when we reach this small number. Yeah, but because I mean, if the angle is even smaller than this, then the case is much easier to handle. So we don't have to worry about it. Okay, so then we have this, then we rewrite these the characteristic of the small, I mean, angular sector or over NLI in this notation. Then we break. We decompose into J, and we decompose, I mean, NLI in two sides with a comparable angle. Then we have to add all these things together. They wanted to bound this. This, I mean, looks very scary, but not so scary. Okay, so But these two sets are bound together. These are diameter 2 to the minus nu and separated by 2 to the minus nu. So actually, even though you have many of them, to control the actual bound, you only have to consider just only 2 of them, right? This is not correct. It has to be soup here. This is a soup over the different angles. Okay, so that means that you only consider this the largest bound, on rotation. But actually, it is enough. Just consider one of such a thing. So then we have to consider summation. But this kind of analysis can be, done without much difficulty, as long as you have this condition. 2 to the minus j is not comparable to square root of mu. Yeah, that means the singular the stationary point is not contained in the spot of this cutoff function. In that case, you can easily handle that. And also, as I already mentioned, the discriminant satisfy this condition, then yeah, you can use the typical oscillatory interval estimate, and then you can prove the desired estimate. So we can handle, this case or either this case. So for that, especially the correct L1 to L infinity bound, we wanted to the bound of lambda to the minus 1/2, right? These are easy, just by using the oscillatory integral estimate, and the L2 estimate, which it can be done by the L2 isometry of the Hermite-Schrödinger operator. So as I explained when I tried to show the result of the Karadijov. Okay, so then you can see that right here in this slide. So we have it here. So because angle discriminant is bigger than this number, that means if this angle is bigger than square root of this number, right, then you don't have to worry about that. So therefore, we only have to consider the case the sector are separated by amount of this. Okay, so the angle actually the angle between these two angular sector 2 to the minus nu. So we only consider that case. The other case can be handled easily, but you need to work to get the correct thing. Okay, so this now we arrived at the core part, the very core part of the whole estimate. So we wanted to prove the estimate over here, and while these are combined together. So, but as I already mentioned, that there is we have very nice rotational symmetry. So you can rotate these tabs together into certain direction, very close to the certain direction. So we always can assume some specific, specific conditions on this set. So actually we decompose this set further. So we have here some cutoff function and another cutoff function. We're going to break this set using some smooth cutoff function. And then we only wanted to prove, need to prove this estimate here, and the additional power here, and the 2 to the minus j is comparable to square root of mu. That's the main estimate you wanted to prove. And why we are assuming this? So why we can assume this? Otherwise, you can prove the estimate without any problem. So repeating the previous argument which I explained. Okay, so and these are adapted to these smooth cutoff function adapted to the rectangles which are contained here, and of dimension. This x1 direction, it has like length of mu, and the other direction, orthogonal direction, you have a length of this, and the other guy as in x1 direction length mu to the mu tilde, and the other direction it has this. Okay, and the naturally adapted to that sort of box means whenever you take a derivative, you got this bound here, this contain is small here, and also this is a very natural condition. Okay, so this might be not so clear, but I draw a picture here to clarify it. So here you have a mu. So this guy a mu tilde. So this is analysis. You have analysis here. So you have analysis here, right? So then we supposed to have the angular sector in certain direction that we rotate it using simultaneous rotation and bring it to in the direction of E1, right? Then we're gonna have some support of this the angular sector here. Then we decompose it further into finer pieces, very, very small pieces, to be at this scale. So maybe some moderating by with some epsilon zero. Epsilon zero is just some quantity specified later. So, but this means you have a small rectangle of dimension this and a dimension this. In x1 direction, you have this length, and the other direction you have this. And also here, because this is a mu tilde, so you have this length in this direction, and that the other direction you have this. So you have a nice, bumper function adapted to this rectangle and this rectangle. That's what you have to do. So that's the case you have to handle. Okay. So all the condition which I mentioned here, this actually reflect this geometry of the underlying set. Okay. Okay. So then in this case, you cannot avoid the zero of the second order derivative. So yeah, but as I already mentioned, to get the correct decay of lambda to the minus 1/2, you need the second derivative shouldn't vanish, right? If that vanishes, there is no chance of getting the decay of lambda to the minus 1/2. That's very important for our estimate, right? So in this case, because we cannot avoid that, we gonna break from that point. So for that, we compute the second order derivative of the phase function. Then luckily we also get similar expression. We get this. This is routine computation. Okay. So then the R xy, this is also quadratic polynomial and with this form. Okay, this guy has two distinct zeros. Okay, so but one of them is bigger than 1. The other is smaller than 1. And the absolute value of this is between 1 and -1. So because here we have cosine s there, right? So actual zero of the this function appear by this relationship. We solve this equation and find it to 0, and just take this guy, smaller one, then we put here, and we solve the equation cosine s equal to this. So then we call this as a second critical point. We have already have a critical point from the first derivative, but this one is coming from the second derivative of the phase function. I'm going to call it second critical point as a C. And but by routine computation, you can easily see this guy very similar to this one, x to the -1, x minus y over to the 1/2. Okay, whenever this guy is contained here, this means because you have this geometry here, these sets are separated by mu, right? Mu. So this analysis is mu. So that means this guy always comparable to something like mu square root of mu, comparable to that. Yeah, whenever this guy is contained, xy is contained b cross b tilde. Okay, so that because to save, this is something we have to do to get the correct decay rate, because you have oscillator integral here, right? This form of oscillator integral here, then if you have vanishing second order derivative, there's no chance of getting the bound lambda to the -1/2. So we have to break away from that. Okay, so then now we have the operator we wanted to deal with, then we break then inserting some cutoff function away from the second critical point. Okay, and also this guy is somehow this typical, I mean, dyadic decomposing function, so right? And then, as I told you, I mean, this everything is actually contained in scale of mu to the 1/2, because so J is like that, and also SC also doesn't move too much. Okay, so if 2 to the minus L bigger than this will escape from the actual, I mean, integration region that becomes 0. So you can impose this condition. Okay, so then, so by simple scaling means, so we scale the S variable because you have a S integral of S here. So you have scale it, and then the kernel of the BL operator is now given by this expression. Okay, this here translated here, and the cosine S is away from the origin, and the whole, so you have phase function here. So this is all composition given like that. So at this point, you can guess what actually happening here, right? So here, so to get the L1 to L infinity bound, you have to estimate this oscillatory integral. Yeah, I take out this guy. I put this vector because the A, if you remember, the A is like a behavior like a T to the minus D over 2. So that this is because of this is a very nice function actually. Okay, so then to get L2 estimate, so L2 estimate, you cannot use the L2 isometry anymore in this form, because this is now disturbed by our change of variable. This guy does not behave very well anymore. So you cannot use the L2 isometry of the Hermite Schrödinger operator. So that's another major problem. Staying away from this second critical point, you save the L1 to L infinity bound, but you have to do some extra work for the L2 bound. Okay, so because of our decomposition, thanks to our decomposition, we have a lower bound, of the second derivative. Then Van-der-Kolk lemma give a very nice bound. So this is what you wanted to have, and some loss here, and this is very good bound. Okay, so but as I already mentioned, the L2 bound become less trivial. So we have to do some extra work here. So here, for the L2 case, we prove this is correct L2 TK late of lambda. So we're going to prove these two estimate here. So even if we can control this, right? So because this function is not totally degenerate, so it has a finite degeneracy. If you have a lower bound of 2L, then still you can get some lower bound of the first order functions. Because of that, this part is much easier to handle because you can do integration by part. This derivative of a phasor function will drop down there, and then this part is easier. This part is actually the main part. It's much more difficult to control. Okay, so once you have these two estimate, you can interpolate them, then you can add up. So the summation along L actually give the correct bound. You see here, you have, a positive exponent of 2 to the L, and here you have a negative power of 2 to the L, right? But this is positive, but this guy contained in this region. So you just count the number of 2 to the L, still you get the correct bound, right? So this will give the required bound for the operator we wanted to handle. Okay, so now the remaining part is proving this. Okay, so for that, okay, so I still have how much time do I have still? More than,
but you can certainly complete.
More than half hours. Okay, so I don't have I only have 3 page more.
Yeah.
Okay. Yeah. So yeah, so from this expression, I mean, this kernel expression, you already can guess. To get the correct, I mean, L2 estimate, you have to handle some oscillatory integral operator, I mean, of this form, right? Cutoff function and some phase here. So that's what you have to handle right here. So for that, so it's defined is we have a cutoff function here and a phase function, which is smooth on the support of A. We define some operator, so putting phase and amplitude together. So I discovered O lambda, so oscillatory integral with the lambda factor. So we have this. Okay, so then this denotes some matrix form of operator. So this is operator. Each of these ij's coordinate, you have this differential operator. This is matrix form of an operator given in matrix form. Then something called a generalized Planck-Serre theorem, which is due to the Perelman. So if the determinant of this phase function does not vanish on support of A, then you can get this bound. This is a very well-known theorem. So this can be proved by, I mean, using some oscillatory integral estimate, and is fairly well-known. Okay, so then you may try to apply this result. I mean, this sort of lemma due to Perelman to control our operator. So if you remember this operator BL, we had a phase function here and also the amplitude function here. So if you go back to the this expression here, these are so all the amplitude is composing all the amplitude, and there's extra S integration. This will be phase function. Okay, so we write that operator in this form. So here phase, amplitude, and S integration. There are extra S integration and this vector here. Okay, so maybe you can try to apply this lemma, but this does not work, I mean, so nicely because our function, I mean, our function and also our phase and amplitude function all depending on mu and mu tilde, right? So it depending on the mu and mu tilde, this operator very, I mean, rapidly changing. So, but we wanted to prove correct a bound, which also depending on mu tilde. So this variation or dependence on mu and mu tilde should be taken into account to control this form nicely. So simply checking this is not enough, certainly, right? So, but this case, I mean, if you have one single function, that's okay. But actually, this is not one single function. This is a function, phase function and amplitude function, which are varying, changing depending on the mu and mu tilde. So especially when this ratio getting smaller, this is even more harder to control, even harder to control. So so because of that, this lemma is not enough. Okay, so how we can handle this situation? So we look at the operator more carefully and try to figure out this, the right dependence of the phase function and amplitude function, dependence on the mu and mu tilde. Okay, so so then we look at the shape of this matrix of the phase function. So we denote this. Here, this SCL, this is actually comparable to, this guy is already I mentioned, comparable to square root of this, right? So it doesn't really causing a serious problem here, but it's actually more convenient to deal with this operator. So you can imagine this is divided here, right? But still, the shape of this matrix actually basically give the shape of this this matrix. Okay, so remove this. Then I this Mij means the ij's component of this matrix. Okay, then xy is in P times P in this set, and also L is a very small, relatively small to this number. Then for any alpha, any multi-index alpha, the derivative of this entity actually behave in this way. So so here you don't have to pay much attention to it, but this is important thing is there is some uniform way, so this matrix entry of all these matrix behave in a certain uniform manner, depending on mu and mu tilde, not so chaotic, right? These are behaving in a certain way. So so you see here the alpha is split alpha 1 and alpha bar, like the x1 and x bar coordinate. We use the x1 and x bar coordinate. This alpha and alpha bar is the remaining coordinate. So depending on the derivative on the variables, we have different structure, different growth rate of this function. Okay, so we will take into this kind of uniform behavior together with some sort of scaling argument to apply, this also sort of oscillatory integral. Okay, so and also most important part is the determinant shouldn't vanish, right? So to apply Hermite type lemma, you should be able to guarantee this guy is not totally vanishing. So when this L is very small, we will use the full, this matrix, full matrix actually non-vanishing. This case, this is a minor matrix of this. Just get rid of the first end line and first column and the first law. That this is the determinant of that. This is not vanishing, right? This is the case. So actually, when L is very small, we only use the not Fourier, variable. We only use oscillatory integral in x bar and y bar direction. Okay, so but I do not want to provide all the detail, but this part we have to work. So this is a significant, even though this is simplifying this way, but in our paper it take up some significant amount of pages. So okay, anyway, so we have this, and also that is not enough. So we have to scale it to make the operator uniform. Then we apply the different form of a different form of oscillatory integral, which this is a certain variant of the Herman's lemma. So here the so oscillatory integral, with a parameter. Yeah. So the omega is very small number. It could be very, very small. Then A is supported in a narrow region. So only X1 region can be very narrow. So this is the d-dimensional ball of radius center 0 and radius 1. And this one-dimensional ball, that means interval region is very narrow. And then the other variable is something like this. And we control derivative. So we're controlled like this. And determinant is comparable to 1. And here, so this is an important condition here. Now we allow this guy, derivative of this guy, blow up in a certain way, right? So and actually we do some integration by part in x variable only. So we only need derivative only beta. 0 and 1th order and 2nd order, but alpha direction we need many differentiation. Okay, so if these conditions are all satisfied, okay, then we still have this the same bound which we already show in the Herman's lemma. Okay, so this mu omega will, in our cases, we will replace this guy with the omega will be like a mu tilde over mu, something like this. We reduce the integral just by scaling and reduce the whole operator in this form. then we apply, I mean, this lemma and get the correct norm. Okay, so here, if I summarize, the specific shape of a matrix M is very important here. And also finally, we need to combine this kind of information estimate together with the oscillatory integral operator depending on one parameter. So that gives all the required estimate. Okay, thank you. Thank you very much.
Any question? From online audience, any questions?
Does your proof also work for special Hermite?
A special Hermite.
Yes.
A special Hermite. A special Hermite. I don't know. I didn't try, but special. What is a special Hermite? Is that related to twisted Laplacian?
Yes, I mean to say twisted Laplace. Yes.
Uh-huh.
Yeah.
Yeah, twisted Laplacian is, yeah, it's much easier to handle. So we already got all the estimate. So all the necessary but the twisted Laplacian, the the spectral projection operator behave not so badly. I mean, here in this picture, right? Here, this is for the Hermite case. Hermite has a bit like complicated picture like this, but special Hermite is simpler to handle. So this operator has a very unique structure because of the potential term. It concentrating near the sphere, but such a kind of thing doesn't appear in twisted Laplacian case.
Is it because of twisted convolution structure? Does it help there? Or are you saying because of the eigenfunction behavior?
Eigenfunction, but the kernel behavior in a much better way. So if you can use the same representation formula for the twisted Laplacian. So using this form of representation, right? You can get the same for the twisted Laplacian. You also use the similar idea. Then you get a form of the formula for the projection operator for the twisted Laplacian. That is much easier to handle. The critical point, behavior critical point, or simpler, but this guy, Hermite Laplacian, has some sort of a degenerate critical point, right? So that make everything complicated.
The question?
Okay, hello. Okay, thanks for your talk. What do you think were needed to address the two-dimensional case?
Could you repeat that again?
Oh yeah, what do you think will be needed to address the two-dimensional case?
A 2D case. So 2D case, we couldn't get improvement of asymmetry improvement. So there are several issues. I mean, because we need to get the bound or when the dpq is equal to 3/2. So in that case, I mean, you cannot add up. In the end of there is very if you follow an old argument or this argument, for the 2D case, you cannot sum these two estimates. I mean, in the right region, you wanted to prove the estimate. So that's one problem. Even if you add up, that the gain of the asymmetric gain is not enough. So we give some thoughts about that, but this argument is not enough. This 2D case become quite certain, I think. Maybe new idea is necessary. A very delicate, analysis, making use of the orthogonality or something like that should be done, I think.
Okay, thank you.
Can I ask something?
Yes.
Yes, sir, with these new estimates for the projections, so do we have some results for the unique continuation also, some new results?
Like
Escariaza has
for
the heat operator.
Heat operator, yeah. So we had some discussion about that, because whether we can use this sort of localized estimate to get a new unique continuation result. But if you are familiar with the literature, they typically use the uniform estimate, right?
Yes.
So I don't think anybody tried to use this sort of estimate. So, but we actually proved something new, because this argument which I explained, which proved the Karadazov result, right?
Yes.
This give the uniform bound in a expanded region. So this is gonna give a uniform bound around this region, wide region. So that was combined with some sort of real interpolation method. We managed to handle some potential which was not covered by Escariaza and Vega.
Okay.
Yeah, so because you can once you have, Escariaza and Vega actually did a 1-point estimate. Because of that, their class of potential was limited to certain class. But yeah, we have estimate in the wide range, so we could use the real interpolation. So that allows us to handle the potential some contained in some weak space.
Yes, the endpoint kind of thing. Okay.
Yeah. But this estimate, but that estimate is not so deep as this one.
Yes. Okay. Thank you, sir. Thank you.
Yeah, welcome.
Hello, hi. So I was just wondering, so when you bilinearize, is there a simple geometric intuition which says that if mu and mu tilde are far from each other, we should expect positive epsilon gain? Yeah, is there a simple sort of geometric intuition behind that? I mean, we know the proof is quite complicated, but
why I was expecting this sort of improvement?
Exactly. Why do you get an epsilon improvement?
Yeah, I can explain that.
Thanks.
Yeah, so that's because of the location of a second critical point. So here, so the second critical point, I just already mentioned, right? This guy is comparable to square root of mu, right? So then the whole integral here. So, and also we know this SC, all these things are comparable to somehow this, and these are comparable to this, right? Because 2 to the j is 2 to the minus j is not comparable to mu. So, but you consider the very symmetric case, right? Symmetric case. So the bound. Where is the? Okay. Yeah, I wanted to go back to the bound here. Okay. So yeah, these are the correct bound without any improvement, right? Right. So, but if if the critical point is close to the, located to the located to the away from the origin, like a square root of lambda, then you actually getting something like this. So d over minus d over this number plus, and there is interval length, something like this. So you're supposed to get this guy in pair case, but because of the distance between this, angular separation, because of we have a separation, this amount of separation, right? That move a critical point to away from the origin, like a square root of mu, right? That replace, maybe I can simply say this. If we do not have any, improvement, we have to deal with fourth of this guy. This guy is mu and mu tilde and 1/4. Then you have to take reciprocal this, but the critical point, allow you just take the integration region is like this, away from, this is distance from away from origin. But this give worse bound, but this actually gives some improvement. So the location of critical point, the second critical point actually give the improvement because the 1 power of the this mu, square root of mu, actually replacing this guy. But the actual, the real picture is much more complicated because you have to decompose further near the second critical point. So all those things are related, but the very basic idea is the decay rate actually controlled by the position of second critical point. Second critical point, if you cannot get any bound, it has to be located, here. But it actually stay away, further away from the origin. That's the key observation.
Thank you.
You're welcome.
More questions? If there are no more questions, let's thank the speaker for a wonderful talk.
Thank you.